In this video, we're going to talk about torque. So suppose that you were disassembling something that had a nut and a bolt, and you needed to get that loose. All right. So you take out your trusty wrench, right? So you put that wrench on there, and then you push as hard as you can, and it doesn't budge, and you just can't get that thing to turn, right? Well, first of all, I was tightening. I should have been loosening, but whatever. Let's do it this way. We're pushing as hard as we can. We can't get it to undo, right? So what do? Well, I know what I would do. I'd get a bigger wrench, right? Why does that work, right? I'm going to put that on there, and then, sure enough, I can totally loosen it. It's actually a heck of a lot easier using the bigger wrench. Why is the bigger wrench easier? Well, that's because of torque. So what's going on here? Well, I think the little guy's a little more manageable here. When I apply a force here, I push downwards, say on this lever, right? It gets transformed into a turning force where this thing is gripping the nut on the bolt, right? Now that nut needs a certain amount of force to make it turn. Right? So somehow I'm translating this force that I'm pushing downwards into a force that will make that turn. Now, if that torque that I'm generating is enough, it'll turn. So the question is, how do I calculate the torque that I generate by pushing downwards on this handle? And so this is an application of cross product, which we're going to talk about right now. Okay, so here we have an application. We have the wrench. And here's the nut. The wrench makes a 30-degree angle with the horizontal. If the mechanic applies a vertical force of 10 pounds on the wrench handle, what is the magnitude of the torque at the point P? Okay, so that if we draw a line from the axis of rotation up to a vector, rather, from the axis of rotation up to the point where the torque is being applied. So this is where we're pushing it down, and we call that vector R, and we call our force vector here F. Then the torque vector is given by R cross F, and so the torque vector actually sticks outwards, orthogonal to these two vectors. All right. So what we should do, though, is we should translate this F vector down over to here. All right. So we'll put it over there. And now we need to compute this cross product. Now, given the information that's here, it takes a little bit of manipulation to get these vectors. Now, one thing you might be saying is that, well, wait a minute, these are two-dimensional vectors. How can we compute the cross product of 2D vectors? Well, in this case, we can do that because we can view this as a two-dimensional plane down here, and we can view a third dimension sticking out of the page. Okay, so we can write down the components of this vector, its x and y components, using the information that's given, and then the z component coming out of the page, we could just have that, well, that would be 0, right? And the same thing with F. We could find its x and y components, and its z component would be 0, right? So we could write down three-dimensional vectors and use the cross product formula to compute the cross product that way. However, there is a more useful formula for us here, and that is the one that describes how we can get the magnitude of the cross product. The formula says that if you have two vectors, A and B, and you take their cross product and then compute their magnitude, this is the magnitude of A times the magnitude of B times the sine of the angle between them. This should look very familiar to you. This should look just like the formula for dot product, except with a sine instead of a cosine. So it's nice that we have this. So this is a very nice way to compute the magnitude of the cross product, if that's what we need. And if you look at this problem, that's exactly what we need. We need the magnitude of the torque. So this is exactly what we can use. So the magnitude of the torque is the magnitude of R cross F, which is, according to this formula, the magnitude of R times the magnitude of F times the sine of the angle between them. Now, what's the magnitude of R? Well, that's the length from here to here. Well, it's a 12-inch wrench. So that is 12. However, remember that in English units, we usually measure work in foot-pounds, right? So let's convert this to feet, all right? So that's actually 1 foot, right? And the force here is 10 pounds. So we're going to multiply that by 10 pounds. And then sine of the angle. Well, we need the angle here between the two vectors, right? Well, I know that this much is 30 degrees, and this is a right angle. So I know that the angle is actually 120 degrees. That is just square root of 3 over 2, right? So we have 1 times 10 times root 3 over 2. That's 5 times the square root of 3 foot-pounds of torque.